All right, 3.9, derivatives of exponential and logarithmic functions, part A. Today we're just doing the exponential part. To start off, here are most of the important properties of exponential functions. Here's a function, or a graph, I mean. This is the graph of e to the x power, and that's what we're going to be working with today. Note, in the picture, e to the x is the inverse. Okay, this means inverse. It is the inverse of the natural log function. The natural log function would be the one down here, which is why if you recall from pre-calculus and maybe algebra 2, e to the x and natural log, they cancel each other out. Okay, so the first few properties are basically what we're going to need to solve equations, right? I started off with the easy stuff. So we might not use all of these today, or but you eventually will. So e to the a times e to the b, since these are exponents and they have the same base, then all I have to do is add them. That's mathematically valid, right? When we're dividing, we would subtract. Again, e to the a is the inverse of the natural log of a. Right? They're inverses of each other, so they would cancel each other out. And the rest is just information about the graph. Okay, example 1. This is not calculus. This is something you should have been able to do last year and the year prior. Solve. 7 equals e to the x plus 1. Okay, so simple enough. Subtract 1, subtract 1. I get 6 equals e to the x. Now, my job is to solve for x. It's always to solve for x, right? So e has to go away somehow. And the inverse of e is ln, natural log. So I'm going to take the natural log of the left side, and I'm going to take the natural log of the right side. And that'll give me, these cancel out, and I have x. And then x is the natural log of 6. If it's required for you to actually provide a decimal, then x is going to equal, and then you're going to plug that in your calculator because you're not expected to know that off the top of your head. X is going to approximately be 1.792. The only e that you have to know is e to the 0 power, right? Because anything to the 0 power is 1. And of course, e to the 1 power, which is 2.718. That's 3 decimal places. Okay, so must know. Must know. Okay. Everything else you're not really required to know by memory. So natural log of 6, if you needed to do that, if you actually had to give me a decimal, it would be with a calculator. Okay, derivatives of exponential functions. So if u is a differentiable function of x, then we have, so on the left we have the derivative of e to the u. So if I have a function that looks like e to the u, when I derive it, I'm going to end up with the original function, e to the u, times the derivative of u. That is the easiest derivative there is. Because whenever I have a function that looks like this, my derivative is going to be the exact same thing, e to the x. Now, when x, or the exponent, gets a little more complicated, then that's when we have to multiply by something. But if it's just x, I'm multiplying by 1, and of course I don't have to write that, right? So this is the easiest derivative, because it equals itself. Okay, now the derivative of a to the u. So this is basically, let me give an example. This is kind of like 12 to the x power. Okay, the u is a function of x, And the a is just a constant or a number. Okay, so the derivative of that is going to be itself, kind of like e to the u, but this one's a little more complicated, a little harder to memorize, but you have to memorize it. So a to the u times the natural log of a times the derivative of u. So now if you really look at these, they are very similar. The only difference is the natural log. Okay? Well, actually, let me highlight the stuff that they have the same. So e to the u and du, here's a to the u, and here's du. So the only thing that's really different is the natural log. Okay, so I can actually do this example, right? No biggie. I guess I should have written it out better. So let's see, example. If this is my function, then my derivative is going to be a to the u, which is the function itself, times the natural log of a, which is 12, times the derivative of x, which is 1. So I don't have to write that. Okay? All right, next. Okay, so example 2, find the derivative of each function. So here we're deriving e to the x, right? So a is y equals e to the negative 5x power. So y prime is going to equal the function itself, e to the negative 5x power, times the derivative of the exponent. Okay, it's kind of like a chain rule a little. Okay, so the exponent, we can call that u. It is negative 5x, so the derivative of that is negative 5. These are easy enough to do in your head, but just trying to make sure we understand what's happening here. And of course, I would appreciate if you rewrote it correctly. Negative 5 e to the negative 5th x power. Okay, B, same idea. This is a fraction, guys. Okay? Don't think, oh my god, that looks funny. So, the derivative is the function itself, as it is written, right? E to the negative 3 over x power times the derivative of negative 3 to the x power. Okay, so like, we can call the exponent u, and then du. I need the derivative of that. It would probably be helpful if you rewrote this. Negative 3 over x is negative 3x to the negative 1 power. Now derive it, because it's rewritten and it's easier to work with. Negative 1 times negative 3 is positive 3. And then x, and then subtract the power, so now it's negative 2. So there's my du, right? So now I can multiply. I can go ahead and use this to multiply over here, right? So 3x negative 2. And again, I'd appreciate it if you rewrote it. Is it a must? The answer is correct either way. So I'll put that in the front, and then e to negative 3x power. Okay. So we're doing the same thing. Example 3, find the derivative of y equals e to the 3x squared power. Okay, so this is all my exponent, right? So y prime is going to be the function itself times the derivative of the exponent. So 3x squared becomes 6x. And so rewrite it so that it is neater. And there is my derivative. If you're wondering, the exponent is the u part, right? And then the du would be the derivative of that. That's how I got my pieces. Example 4. Find the derivative of y equals x squared times e to the x minus x times e to the x. Okay, so a little longer, but the purpose of this example is the fact that it has a product rule. Because I have x squared times e to the x, right? So there's my two functions. And then I have x times e to the x. So I have two other functions. So this is product rule and product rule. So u times v and another u times v. Okay, if you want to list everything out, please be my guest. But at some point, I feel like you should be able to do the product rule without listing everything out. All right, so I'm going to do the first part. I'm going to do that in red. Actually, here's y prime. So eventually, I'm going to end up with a minus, right, down the middle. Okay, I'm going to do the first part. So u times v prime. So e to the x is v. So derive it. Oh, e to the x is e to the x. Gotta love it. Plus v, which is e to the x, times u prime. So that's 2x. So there's all of this here. Now minus, right? There's my minus right here in the middle. That's where I got my minus from. Right? Nice big fat minus. And now I'm going to do this part. All right, so u, that's x. Let me put parentheses just to be safe. Times v prime, it's just e to the x, because the derivative of e to the x is e to the x, right? Plus v, which is e to the x, times u prime, which is just x. The derivative of x is 1, so I don't have to write that. Okay, now I'm going to be a good little girl, and I'm going to distribute this negative. I could have probably have done that with the u to the v, but I decided not to. So simplify whatever you can. Let's see. I have x squared e to the x plus 2x e to the x minus x e to the x minus e to the x. Let me see if I have anything that can be combined. I see that I have a negative x e to the x and I have a positive 2x e to the x. So basically I have like two of these things, whatever they are, and then I have a negative 1 of these things, okay, whatever they are. So 2 apples minus 1 apple, basically. And that's the only thing I can simplify, and that'll be it. So that, my next line is my answer. So x squared e to the x. So I have 2 minus 1, so that leaves me with just a positive 1. X e to the x minus e to the x. These all have e to the x's. I can probably factor them out, but I don't see any purpose to it. So therefore, this is my answer, and I'm done. All right, now we jump to the derivative of a to the x, functions with the x, or where the x is the exponent. So find the derivative of y equals 9 minus x. Now, let's recall. The derivative of a to the u is itself times the natural log of a, which will usually be just the number, times the derivative of u. Okay? So here, let's break this down. A is the 9, the constant. U is the negative x. And then du would be the derivative of that, which is just a negative 1. Okay, those are my pieces. So, y prime equals the function itself, 9 to the negative x power, times the natural log of 9, times the derivative of u, which is negative 1. And the only thing you can really clean up here is the negative. We can just call this negative 9 to negative x power times the natural log of 9. That's pretty much it. That's all I'm really going to ask you to do. For example 6, they're asking us to find the derivative of y equals x to the 1 minus e power. I encourage you to try this on your own before listening to me do it. So this would be a good opportunity to pause. Hopefully you can do it by yourself. Okay, so example 6. We're finding the derivative here. This is not a to the x. X is not the exponent. The only thing that I see is that there's an e in it. Hopefully you could see that this has no connection to the prior 5 examples. I don't need e to the x, the derivative of e to the x, and I definitely do not need the derivative of anything that looks like a to the x. This is something that I believe you should have been able to do before the lesson. So what if e is there? E is like pi. It's a constant. And we constantly get confused by e and a pi and things with letters in it, like natural logs. Those are constants as well. All right, so here I have x to some power. Well, our rule for things to powers, right? Our power rule is you bring the power to the front to multiply. So 1 minus e multiplied by x to the 1 minus e power, but then I have to subtract an exponent. Right? That's our power rule. You bring the exponent to the front to multiply, and then you subtract an exponent. And that's what I just did. And that's basically it. Okay, so 1 minus e, and then x. And as you can see, I have a 1 and a negative 1, so they cancel out. So I'm just left with negative e. And if you really wanted to, you could rewrite this as 1 minus e over x to the e to make the exponent positive. Same thing, same idea. All right, last example, example 7. At what point on the graph of the function y equals 2 to the t power minus 3 does the tangent line have a slope of 21? Okay, so first of all, this function is basically a to the u minus 3. Okay, so that's what how we're gonna derive. That's an a to the u, right? Because the exponent is the variable. So I'm trying to figure out where the tangent line is going to have a slope of 21. Okay, so there I wrote basically a translation of what this is saying. At what point on the graph of the function does the tangent line have a slope of 21? So where does the slope equal 21? In this class, slope is derivative, right? Derivative. Okay, where does a derivative equal 21? And we're looking for a location, a point. So that means I need an x and I need a y. That's what we're going to do. So first thing on the plan here is derive. Take the derivative of y. So y prime equals, all right, 2 to the t minus 3. We should all know what happens to the minus 3. Becomes 0. So I'm basically deriving 2 to the t power. So the derivative of that is the original function, 2 to the t, times the natural log of 2, times the derivative of t, which is a 1, which, yes, I don't have to write. So I'm just going to erase that. Yay! So there's my derivative. Okay? Now, my job is to make this derivative equal 21, because I'm trying to figure out where does this happen. Where does the derivative equal 21? So I have to make it equal to 21 in order to find out where. Okay, so 2t, oh, that's a big T. I didn't mean to write that. Big 2t, right, times the ln of 2 equals 21. So I'm going to solve this. And this does require some stuff that you learned last year in pre-calc. And probably algebra 2. I'm not sure. I think you learned this stuff in algebra 2, right? Okay, so as always, the variable is what I'm trying to get by itself. So first order of business is I'm going to divide by the natural log of 2. Both sides. That gets rid of that. So I have 2 to the t power equals this funky looking fraction. All right, now I have the problem that t is an exponent. So I need to figure out or remember how to get rid of like my base. How do I make that exponent into the actual number I'm looking at? Okay, now the answer is not very hard. What you're going to do is you're going to use natural log. Okay, you're going to use natural log. You're going to natural log both sides. So let me rewrite this so that I don't make a mess. I'm going to write it out a little bit to the other side. Okay, so I'm going to do the natural log of the left side, and I'm going to do the natural log of the right side. Okay? Alright, so then now this is going to require remembering some rules, and I'll go over them again on the next, what do you call it, notes, right? Natural logs, right? Logarithms. You can rewrite certain things, right? For example, this exponent for natural logs, it is valid to bring that exponent and plop it right in front. Don't know if you remember that. And for natural log, right? For natural log, if I have the natural log of a over b, I can rewrite that as the natural log of a minus the natural log of b. Okay, and what I just wrote about the exponent, the natural log of a to the b, that could be rewritten as b times the natural log of a. Okay, these are just reminders of stuff you should kind of already know, somewhere in the back of your brains. All right, so I'm bringing that to the front. I end up with t natural log of 2 equals. Now, the 21 is being divided by the natural log of 2, so I can split this into the natural log of 21 minus the natural log of the natural log of 2. Okay? All right, now the purpose of this was because this dude right here, I needed him not to be an exponent anymore, and he's not. And now I can just do math, and I can divide this side by the natural log of 2 to get rid of that. And of course, whatever I do to one side, I must do to the other. Now, this is going to require your calculator because I do not expect you to do this in your brain at all. So what I have is t all by itself, yay. And then I have the natural log of 21 minus the natural log of the natural log of 2 over the natural log of 2. And you would plop this into your calculator. Okay? And you would get decimal that looks like this. And that is t. Okay, I need a point. The whole purpose of this problem was to get a point, an x and a y. I guess I should have said t and a y, because they did use the letter t, right? So my t is, let me go back down, 4.921. Well, how do I figure out y? Well, let's see. This function here is y equals. So in order to figure out y, I'm going to take my t and I'm going to plug it in. Okay? So find y. So y equals 2t, or 2 to the second power, boy, 2 to the t power minus 3. Then using your wonderful calculator, you would get the original decimal that you got. It's a really long one, right? And you would plug that into t. I'm just going to do 4.921, but you should use the original decimal because I didn't write it down. Bad girl. All right, so that's what I'm going to plug into my handy dandy calculator, and I would get this number, 27.296. That is rounded to 3 decimal places, as you should in this class. So, my answer at 4.921 27.296. Um, the tangent has a slope of 21. And there you go. Please do your homework.